everyone, and welcome to today's Universal Chiplet Interconnect Express's webinar, The Growing Chiplet Ecosystem, Collaboration, Innovation, and the Next Wave of UCIe Adoption. A couple of housekeeping things before we get started here. This webinar is being recorded, and both the recording of the webinar and the webinar slides will be made available on the UCIe website later. We encourage you to share this webinar with colleagues who may not have been able to join today. Time permitting, there will also be a Q&A at the end of today's webinar. So if you have a question, please submit it via the Q&A tool that you'll find at the bottom of the Zoom menu. Now, with all of that said, I'll turn it over to today's moderator, Brian Ray, UCIe's Marketing Workgroup Chair. Thanks for joining us today, Brian.
All right, thank you for joining, everybody. So I am Brian Ray, co-chair of the UCIe Marketing Working Group, and also an ecosystem manager at Intel. So, as you heard in today's webinar, we're really going to be digging into, what's driving UCIe adoption, how companies are collaborating the ecosystem to unlock innovation with chiplet-based architectures, and what the future looks like for chiplet-based systems. So joining me today, we have a distinguished panel of UCIe member companies. So we'll do a quick round of introductions, starting with Archana.
Sure. Hi, good morning, everyone. My name is Archana Cheruliyil. I'm a product line manager at Alphawave Semi. I manage the portfolio of UCIe, HBM, and 3D IO IPs at Alphawave.
Very good, thank you. Next is Justin.
Hi, I'm Justin Bunnell from Siemens EDA. I'm a technical product manager at Siemens, focused on verification IP, specifically UCIe, UA Link, and some custom verification IP solutions.
All right, thanks. Next is Manuel.
Hi, good morning, everybody. So my name is Manuel Mota. I'm a product manager at Synopsys. I'm in charge of all the die-to-die interface IPs, solutions, and also, of course, focus right now is mostly on UCIe.
Very good. Next is Mayank.
Hi, everyone. My name is Mayank Bhatnagar. I'm a director of product marketing at Cadence. At Cadence, I manage all the die-to-die interfaces, including UCIe.
All right, thanks. And then we have Vishal.
Hey everyone, I'm Vishal Chandrasekar. I'm the Director of Product Management at Ayar Labs. And what we do is build co-packaged optical engines for scale-up connectivity in AI networks. So I'm really looking forward to the discussion and talking about how critical UCIe is to our products and roadmap.
Awesome. All right, thanks everybody. So it's a great panel of companies that are industry leaders and are very active in UCIe. So you're going to learn a lot today. So let's get started. Chiplet-based architectures are definitely on the top of mind for chip designs today. So to kick us off, let's start with Manuel. What do you see that's fueling the momentum behind UCIe adoption, across the ecosystem, all the way from IP vendors through system integrators?
Yeah, I mean, clearly, I think what we see is UCIe is the facto standard today for the industry for die-to-die interfaces. It has achieved broad adoption. We see it across the board with our with companies working with us, and that is due to the very compelling technical metrics, the flexibility that it fields to address the requirements of a wide variety of use cases. I'd say it. Additionally, it offers a very clear path for chiplet standardization. It does not cover only the die-to-die interface, as we well know. It also goes beyond that into the full chiplet and covering full chiplet and system level as well, right? So that's also addressing very important aspects for multi-die SoC operations. I mean, we can talk about manageability, we can talk about testability, security, etc. All these aspects are being covered by the UCIe standard, making it even more relevant for multi-die systems. And that's how we're seeing. We see also, the fact that UCIe standard offers high modularity. It enables the different use cases, and that also helps adoption across the different applications, across the different market segments.
Okay, yeah, very good. And I think so. Yeah, it takes community, takes industry leaders to to develop the standard, but then to implement products. So building off of that, we've got UCIe with up to a 3.0 specification at this point. So next, I'm kind of interested to hear how you're seeing the industry collaborating to advance real-world chiplet solutions. So why don't we go to Vishal next and hear what your perspective is.
Sure, yeah, I can take that. So Ayar Labs, like I said, we build optical chiplets for scale up, and what that means is connecting up hundreds of GPUs to work together in a single domain, very tightly coupled. And we do that through optical connectivity. And so essentially what our chiplets does is connect up GPUs to switches, converting electrical data from the GPUs into an optics and pipe it over to switches or GPUs and deconvert it back. And we have really committed the electrical interface, the part which talks to the GPUs and switches. We've really committed that part of the roadmap to UCIe. And the reason for that is, UCIe gives the best in terms of bandwidth density, low power, and low latency, which is very critical for these scale-up applications. And so, we had our first UCIe optical chiplet, which we demoed in Q1 of this year at OFC. And we made a collaboration announcement about a month ago at the TSMC OIP event with Alchip, which people might know as high-performance ASIC designer and packaging. They do a great job at that. It's selling into hyperscaler customers, so really designing their ASICs for really large-scale deployments. And we announced a collaboration of a product that we will be bringing to market, which basically pairs the ASICs coming from Alchip with the optical engines coming from us, and being able to connect up large numbers of these ASICs together. And so the form factor that looks like is probably something people recognize. It's like above my shoulder here, but it's basically the center is sort of a typical AI accelerator with the accelerators and HBM and so on. But along the edges, you can see the optical chiplets. And the key point here is that the interface between that accelerator and our chiplets will be UCIe for the bandwidth, latency, power reasons that I talked about, but also because the great part of UCIe is that you take two companies with very different technologies and skill sets, indeed different process nodes, and they're able to work together to bring their own skills together to bring a very valuable product to market, which is the key selling point of UCIe. And as Manuel said, there's widespread adoption of UCIe as the best standard for this purpose. So this is a collaboration we're very excited about, and we will be bringing it to market in the coming months. And it wouldn't be possible without UCIe.
Awesome. Thank you. Yeah. So kind of taking this, from that point, whether you're a single company designing something or, really looking at different, functions that you want to integrate onto a package, a silicon ASIC, you can really look at how ecosystem partners can leverage the UCIe standard to manage, as they're designing, how do you have an efficient die-to-die interface, manage the overhead while maintaining interoperability and performance. So I'm interested to hear perspective on how companies can think about that. So Archana, would you like to take that?
Sure. Yeah, I think I want to address this from a power efficiency standpoint, because I think it's really emerging as one of the biggest differentiators when you talk about chiplet-based systems, especially as data movement starts to dominate, total system power. What's really good about the UCIe framework is that it's powerful that it gives the customers a common interoperable baseline, so partners can focus on innovation and power optimization rather than reinventing the interface itself. So for example, in a closed ecosystem with UCIe, it provides the flexibility to build tailored implementations where you can optimize, for example, the link width, you can enable voltage scaling or protocol layers while still maintaining full compliance at the PHY and protocol boundary. At the same time, your UCIe spec includes robust testability and debuggability features like loopback testing, lane margining, and link training protocols, where really simplify the power tuning and validation process across your vendors. So instead of debugging the interface itself, you're able to spend all of that energy fine-tuning power and performance for a specific application and specific form factors. I think ultimately, UCIe provides a very stable platform where everyone gets to innovate above the standard. And that's how we make meaningful progress, I think, as to reduce interface overhead without sacrificing interoperability.
I would like to add something here, if I may. So for the power efficiency and other factors, right? One big benefit that we see with UCIe definitely is that it gives that stability to new designers. Because right now there are a lot of optimizations and, like as Archana mentioned, customizations possible. But for anybody that is adopting UCIe today, they want to make sure that whatever they design over the next 2 to 3 years will remain usable, interoperable over the years. So I think UCIe gives that stable framework and the background and the confidence for people to be able to use it as it becomes adds more options, or for example, it optimizes on things like power, which is obviously extremely important.
Right. Thanks, Mayank. And yeah, let's just keep kind of going with this a little bit. So you've got a baseline. We're not reinventing the wheel, but people still want to tailor their implementations for specific design needs without sacrificing performance or interoperability. We as you're kind of alluding to there. So I'm kind of looking for some other perspectives on that. Maybe Justin, you want to take that next?
Yeah, sure. Being in verification IP, we work with lots of different customers that have, various different requirements for their chiplets. And so a lot of what, like Archana said, and Mayank, we see customers trying to optimize for their bandwidth requirements, for their power requirements. And UCIe has a lot of options built in. So, you can support different packaging types, whether you're doing a standard package, trying to keep your costs low, or your lower performance applications. You can do advanced packaging. And then with UCIe 2.0, there was the introduction of support for 3D packaging, even if you have ultra high bandwidth requirements. Another area we see people utilizing the flexibility of UCIe is in their protocol selection. So UCIe natively supports PCIe and CXL as a protocol layer, but it also offers a lot of flexibility for the types of protocols you can drive over your die-to-die interface by offering raw streaming, where you can just send any protocol without utilizing the die-to-die adapter for link reliability. But then we can also use streaming protocols where you can map any protocol to a particular flip format, and then utilize those die-to-die adapter features as well to make sure that you have the
I've lost you there, Justin. Oh, there we go.
Okay.
Cut out for just a half second. Yeah, go ahead.
Okay. So yeah, we do see customers using all of these different protocol options, and then the other area is also just in optimizing for bandwidth and power. So UCIe supports all the way from 4 gigatransfers per second up to 64 gigatransfers per second with the 3.0 specification. There are customers that maybe, depending on the process node that they're developing in, might only be able to support a lower range. But they're able to interoperate still with other chiplets, that may support a higher max link speed. There's also optimizations you can make in terms of the link width. So UCIe supports 64 by 64 by 32 by 16 down to by 8, depending on how much bandwidth you need across the link. And then just on top of the flexibility of the standard features, there's also lots of optional features that have been added to the specification from 2.0 and 3.0. So there's, as I think Manuel mentioned earlier, system and package management protocols. There's DFX features that are kind of addressing more of the system level requirements. When you're trying to build system and package with multiple chiplets involved. So all of these different features we see customers using, either some of them or all of them or none of them. And yeah, there's really a wide range of implementations that can be addressed with UCIe.
Yeah, thank you. Yeah, please. I was going to say, anyone else wants to add on to that, please.
Yeah, I want to reinforce this point and to bring in the multiple use cases that are out there, and in a sense, we are in the die-to-die world. We are not in a position to say one size fits all. You don't have one solution for all applications. But what is interesting with UCIe is that it enables us to support all of them through the different options, through the different features and form factors and speeds and protocols that it enables. and so in a sense it's key for for us as implementers of UCIe to have solutions that are flexible enough to go after all these optimizations and all these different use cases with implementations that are specific for them while staying within the UCIe umbrella as we were discussing.
One thing that I would like to add is like some optional features such as, for example, UCIe supports multi-protocol enablement. So where essentially you have two protocols going into the same file. So those do allow a lot of improvement in terms of or optimization in terms of, say, power and latency. For example, if one side somebody wants something that is very mature, say a PCIe, but then as a regular traffic, they want to use, say, the ultra low latency that streaming affords, they can essentially put those two together where they use PCI for, say, bring up in ways they know and for debug. Whereas for normal traffic, it goes to streaming. So those kind of optional features of UCIe are definitely helping to improve the PPA of the overall use case.
So that's illustrates the strengths of the specification for delivery capabilities, but critically, that it really enables interoperability so that you can pick best of class chiplets when you're putting together a solution. So next I kind of want to look then at how is this looking in examples from the real world of partnership projects or products that that some of you have been participating in, where we see the interoperability leveraging UCIe, and what are some learnings that you have from both your own company, but in working across the industry, to support customer designs. Does anybody want to jump on that one?
So I can mention one example we recently had. So over the last 2 years, we have been working on UCI interoperability with Intel, where Cadence's UCI IP interfaced with Intel's UCI IP. So both independently designed in different process nodes. We put them together on a test chip and with the common packaging. So, and that shows that, okay, so what are the issues with PHYs, or for example, where they are compatible, where they may not be. One thing that definitely is of note is that UCI interoperability by its very nature needs the creation of a test chip and packaging. So which makes it inherently different than, say, for example, a PCI plug fest, where you can essentially plug two boards together and see interoperability and then unplug and then check with something else. So this leads to inherently longer timelines and cost associated with the interoperability. So what we also did was we did a pre-silicon work where we did a co-simulation setup, and we were able to not only check the sequence that will happen after silicon, we were also able to forecast any differences that we may see. And then essentially that helps speed up the post-silicon interoperability. And as for learning, we did publish a white paper in 2024 in initial stages of our co-simulation. We also had a tutorial on this topic in Chiplet Summit earlier this year, where we talked about how the core simulation can be set up, and that is something that anybody can set up. And we want to make sure that our learning is also used by others to set up similar things. And we are also we did promote and publicize the fact that we had completed that silicon interoperability. So we had that joint presentation in Cadence Live, and we are also working on a joint paper to make sure that this knowledge that we have gained is used by everyone who is looking to use UCI and see how far along UCI has come and how the interoperability is working.
Yeah, and I'll just jump into and follow on to what Mayank said about needing to kind of shift the interoperability testing forward, without the need to have a test chip. And Siemens EDA, Alphawave Semi, and Ayar Labs, where we were able to take those two chiplets from those two companies, both UCIe based. Alphawave had a UCIe IO chiplet, and Ayar Labs had a had a retimer chiplet, optical retimer chiplet. And so Siemens EDA, with using our verification IP, we were able to drive stimulus and co-simulate those two chiplet designs together and prove interoperability testing in simulation at both the PHY and controller level. And one of the unique things about UCIe is that UCIe, not only defines the PHY interface for the die-to-die interface, but also defines, the FLIT-aware die-to-die interface for the protocol to adapter, and then the adapter to PHY interface as well. And so we're able to, with the verification IP, verify not only the PHY interoperability, but also the interoperability between the FDI and RDI interfaces as well. And so that just, reinforced to us, that's possible when you have a really well-specified interface and protocol. And then, just also enables us to shift that interoperability testing earlier. And so, apart from just doing simulation-based compliance testing, with verification IP to IP, actually bringing together different chiplet implementations in simulation early and improving that interoperability at an early stage.
Yeah, I could just echo what Justin said. So yes, we did this, interoperability with an Alphawave chiplet and our chiplet via the Siemens EDA verification platform. This was really critically important to us and very valuable. Because taping out chips is expensive, both in terms of time and money, but also maybe most importantly, time to market. We have like yearly cadence of products coming out now in the market. And so if you make an error or you need to do a respin, that you're often off by a generation, and that can really be expensive. So being able to prove out the functionality of the chiplets in a simulation environment is absolutely critical, which is what verification is, but is even more critical now because we are building the electrical interface in our chip really by ourselves. And so to be able to prove that it works on a different process node and an IP developed by a different company, in this case Alphawave, to show that we're able to make our chip work with their chip and talk to it and function was absolutely critical. And so I think interoperability is critical for any consortium or standards-based implementation. Plugfests, like what Mayank said, are critical for widespread adoption, reducing costs, reducing risk to the end customers, and so on. But I think it's particularly critical in these sort of chiplet environments, or chiplet implementations, which are so complex. So I think this was a great opportunity for us to learn. It really helped us debug a lot of issues pre-silicon, as Justin said. And so it helped ensure that when we did tape out, we were able to get success on the first version of our chip, which came out. So I think it was a great example of collaboration.
Awesome.
Yeah, and I'm gonna just concur with what has been said here. We at Synopsys, we also identify this as a key and critical activity to foster the ecosystem. We've also been involved since a long time in deploying with partners interoperability events or exercises, call it like that. Some of them are public with Intel as well. That was a UCIe on an advanced package, but we continue working with other partners. We do it also. That was a hardware-based event or exercise, but I think, as has been said here, Mayank stated that, and I agree. The software simulations and Justin as well, software-based simulations and perhaps simulation as well are other opportunities to get to help verifying and interoperability in a lighter, lower cost way, which which de-risks in the end the manufacture of the system, like Vishal you were explaining. So we have been working actively on solutions for all these domains with our partners to ensure that the ecosystem is safe and can work with the interfaces from different vendors. I would just add on this beyond Synopsys or any of us here. we see this as a I mean, the industry clearly sees this as an important aspect. We see it we see ecosystems across the industry being formed. You know, be it on the automotive space, that's an area where clearly, you know, small local ecosystems, however we want to call them, are appearing with the specific purpose of ensuring, you know, that that different companies can work together, can verify their interoperation, and building upon UCIe, building upon UCIe spec additional you know, additional specifications that are more suitable for, or more targeting their applications. And this is in fact also one of the beauties of UCIe. It allows other applications or application-specific specifications, if you will, to be built on top of it and to leverage the great benefits, you know, the great properties of UCIe, be it flexibility, as we said, lightweightness, etc.
So yeah, so I think just kind of going back to several of the points that were made. So, you know, the first, you know, the you know, companies that are you know, leading UCIe are leveraging a lot of experience from other, you know, industry standards, you know, where we are, you know, designing you know, what goes into the spec very thoughtfully, and then also putting in the hooks that are, you know, needed for ensuring interoperability, and, you know, thinking through how would you look for you know, testing and compliance. And so, you know, definitely the stakes are higher whenever it's you know, packaged into a silicon product versus, you know, an add-in card that was mentioned. And so, you know, there's certainly a lot of attention in the industry, you know, now about the possibilities for simulation, emulation, and all the way from the chip level up to, you know, data center levels. And I think that's you know, it's another, you know, important trend, and, you know, that feeds into helping people, you know, be successful. But knowing that you're building off of, you know, not something that you've had to invent yourself, but there is a standard, and there are multiple vendors with real world examples, and they're proving it out, you know, increases the you know, the confidence in the individual chiplets, and in the standard itself. So that's been, you know, what's really been exciting for me, watching UCIe get off the ground, and, you know, over just a few short years, getting to this point where we've had some of these real world interoperability projects where, you know, then you can get to actually having silicon that you can hold up and show that it works, and that your you know, what you did in simulation, you know, paid off, and here, and, you know, powered on, you know, successfully, and you've already addressed some of the issues that you might have otherwise not found until you powered on. So it's been a lot of fun watching those projects. I think the other thing you mentioned was you know, the different spaces. So everyone's, you know, certainly aware of AI, and it's you know, pushing the boundaries of you know, functions, capabilities that are needed in chips. So that's a natural place for chiplets. Automotive, we have an automotive working group, so in UCIe, so we're thinking about you know, how do we you know, make UCIe good for a variety of segments. Are there any other application areas or market segments, Manuel, or anyone else that you see you know, getting some movement right now?
Well, I would say that, I mean, clearly the data center, the HPC space, the AI, you know, segments. This is where the adoption has, you know, has been overwhelming for multi-die implementations, and relying on UCIe, on the UCIe framework in any case, to solve their die-to-die interface, you know, problem, let's call it. I think today it's a reality. The vast majority of server AI training and inference SoCs, you know, network switches, etc. They are leveraging this type of architecture. They are leveraging UCIe to solve their problems. And UCIe in itself as well has evolved to support this very demanding application. Right, we are now with UCIe 3.0. We are now going into very high bandwidth efficiencies with 64 gigabit per second or the transfer per second per pin. We're you know, supporting 3D as well. So all of this is both feeding and, you know, and being fed, if you will, and getting feedback from from the applications to evolve and support the industry as we go along. As you mentioned, I think the other areas where we at Synopsys see also growing adoption of multi-die architectures and UCIe is on automotive. I think that specific in ADAS type of applications, I think this is there's a clear trend in that domain for multi-die implementations. But others, like on the edge AI kind of space, robotics kind of space, we do see multi-die and you say starting to be deployed as solutions for for also their more demanding implementations.
Okay. Anybody else want to add
Sure.
another one?
Yeah, I'd like to add some. So I think to add to Manuel's point, I think as part of UCIe 3.0 enabling 64 gig, we're seeing a lot of requests, especially across form factors. So if you look at standard package implementations of 64 gig, we're seeing a lot of customer demand around IO chiplets and optical chiplets, specifically co-packaged optics. They're really leveraging bandwidth of a 64 gig bump out, right, of the IP. These can enable all the way up to like 16 tera total bandwidth aggregate bandwidth density. That's really critical, I think, for IO chiplets, specifically when you start to integrate optics onto the same package. When you look at advanced package, for example, high performance switches, right, or network processors where you're moving massive amounts of data between quadrants of a die, where you're looking at bandwidths as high as 100 terabits per second, right? This is where I think 64 gig becomes a very critical enabler. And even beyond IO disaggregated systems, I think when you look at memory, right, we are seeing a lot of implementation around high bandwidth memory where a custom based die implementation is emerging, and it's being kind of powered by UCIe, where you can leverage a UCIe die-to-die PHY to reduce the overall silicon footprint on the IO interface. And it can also help recoup some of the shoreline on your compute die, which can allow for additional logic to be integrated onto the compute die, which most likely is on a more advanced process node. So it's bringing in more compute, reducing cost, improving yield, and it also helps for customization on the base die itself, making it a more tightly integrated system. So it's not just helping with IO, but I think it's also massively, informing how the memory traffic and alleviating some of the bottlenecks that we're seeing in today's AI systems. When we talk about 64 gig, I would be remiss if I also didn't touch upon from an IP perspective, some of the challenges, what it takes to kind of implement a system at 64 gig performance. So for example, at 64 gig, right, we are implementing features like advanced equalization and tunability, specifically to kind of meet the spec and maintain signal integrity across the channel. But each of these costs, each of these features comes at a cost, for example, in terms of power and complexity. So the design challenges do remain at 64 gig. But ultimately, I think, as the ecosystem matures, as we adopt more 64 gig based UCIe IPs, it is going to become foundational building block, not just for memory and compute scaling, but I think also connecting newer features and domains like optics and accelerators. So I think, as companies make more strides towards understanding the full end-to-end 64 gig UCIe channel, it's going to be imperative, I think, in terms of next generation AI systems. It's going to be a key building block.
I would like to add something onto the market segment question, Brian. So one thing that we see is, one, of course, the reason for going die-to-die or multi-die design is when the design does not fit into a single die, right? For yield reasons, or it's simply too big to be on a single die. So that is the classic HPC use case or the AI use case. So we are seeing UCI used for that. There, the usage is homogeneous in the sense that there are multiple dies essentially cut out of what was supposed to be a monolithic die. Then when it comes to applications such as automotive, there is a slight difference we see. It is not that the design is too big to fit on one die. There, the reason for going for multi-die is to stay with, say, more mature designs for things like RF and analog, which don't really scale with the newer technology. So there, the reason for going multi-die is risk reduction rather than simply splitting between the dies. So we see multiple market segments being serviced by UCI, but for different reasons. So for example, For automotive, with heterogeneous integration, their interest in, say, merging very old technologies with very new technologies. And when I say very old, very new, it's all relative. The technology is moving so quickly that even something that was just 3 years out now seems like very old. But their interest with heterogeneous integration and also their interest in wanting one piece from one company to work with another piece from another company is, I believe, what is driving interoperability even more than HPC users, where they usually own both sides of the link.
Yeah, and I can just sort of add to that. I think everyone did cover the applications well. We see so much in the automotive space and like mobile SoCs and such for the reasons highlighted. I mean, we can talk about what are the key reasons people use UCIe. It's basically, as was said, different process nodes, different companies with different technologies. But within the AI space, you can say, which is sort of in vogue right now, really the key mantra over there has always been highest bandwidth density, low power, and low latency, and that's certainly what attracted us to it. And so for things like optical I/O between GPUs and switches, like Archana mentioned, and going forward even for HBM implementations, I've seen data showing that it is competitive or better than the standard HBM spec in terms of bandwidth density, power, latency. And so those are applications which I think we're going to see shortly. And we at our labs, we even see applications to take that one step further to combine the power of UCIe and optics for an extended memory, because really the amount of memory per GPU is sort of the bottleneck that people have identified. You really need a lot more memory per GPU, which even HBM, the advanced HBM implementations cannot meet. And so you can now, thanks to the power of UCIe and optics, connect up more HBM through to memory via a very low power, low latency, very, very high bandwidth link. And so we see a lot of interest in combining the power of UCIe and optics in order to achieve that. So I think that is something also we will see in the coming years. I really am amazed at the number of applications that UCIe I see being announced and coming to market. I think we're going to see a lot in a variety of fields in the coming few years.
Okay, very good, thank you. And I see some questions coming in, so we'll circle back around to those here in a minute. I'm just kind of thinking through how to pace that out. We've covered a lot of ground here, so maybe just to wrap up, this piece, and then we'll maybe turn to some questions here in just a minute. Thinking of everything that was just said, maybe Mayank, you could help us kind of take a pulse. Like, what did we just hear? What are some key takeaways you would like the attendees to hear about UCIe's readiness and the long-term suitability for enabling an open chiplet ecosystem?
For sure. Thank you. So UCIe is now more than 3 years old. When UCIe started, of course, the adoption was by, say, people that were already using some custom die-to-die interfaces. The initial question obviously was, will UCIe match the PPA of those interfaces and things like that? Over the years with UCIe versions, version 1.1, then 2.0, and this year 3.0, UCIe has shown that not only it is able to come very close to those custom applications, but with industry's best mind putting their minds together, it is also able to develop a lot of these optional features. Like we have in 2.0, we have the MTP feature. In 3.0, we have multiple more features added. So with these optional features, we are able to create a UCIe which is able to be diverse and meet everybody's requirement while on its own being a very lightweight application. So you can have a UCIe which is bare bones, just streaming interfaces, as was earlier mentioned, and essentially use it as just a pipe. You can obviously put multiple protocols on top of it. You can even put anything proprietary on top of it with a standard interface that UCIe provides. So with that flexibility that UCIe has and the adoption that we are seeing all the top users of die-to-die interfaces adopt UCIe. So with that kind of adoption, that kind of industry support behind it, UCIe is definitely poised to be the de facto interface. And with the flexibility it gives, UCIe is truly becoming universal, as the first letter of the acronym says.
I like that. Thank you. You touched on this. I see a question asking about some specific other interconnect technologies. So I won't comment on anybody's proprietary interface and what it does or doesn't do. You'd have to ask that company. But what Mayank alluded to is UCIe is going to provide complete solution, electrical protocol, manageability, test, security. We're thinking through all the dimensions that someone would need to leverage, particularly for interoperability for building chiplet-based systems. But what you've also heard is that there's some modularity. So, for example, at the protocol level, people picking their own protocols that they want to put on top of UCIe. So there are some examples, in the Q&A of some where that is not only possible, but you can read papers from industry conferences, or here's some specific examples, and I think you'll hear even more coming forward. So that's one thing I see in the Q&A. Another thing, there's a technical question. I'm going to see if I can find an answer to you for you while we talk. If not, you might have to. If you're not a UCIe member, please join, and you can come into the working groups and have those discussions. But you can also reach out to us through our website and ask your question, and we can get it to the right person. If I knew how to follow up, I would with you here. If you want to leave your email in the chat, I'm happy to take a technical question like that. So let's see, there is something else that I want to come back to. Okay, so there's a question about other market segments beyond HPC automotive, particularly it says handheld products benefiting from multi-die architectures with respect to power efficiencies, data rates, bandwidth, packaging technologies. So yes, so UCIe is addressing best-in-class specifications with input from members across the industry, so that we can try to make it something that is not everything for everybody, but basically so that it's going to provide a range of choices that people can implement in different market segments. And that goes from standard packaging to advanced packaging to 3D stacking to the 64 gig speeds that we talked about. But I'll just open it up to anybody on the panel here if you want to comment on kind of what you see for either handheld or other low power or even more commodity type chiplet based opportunities.
I can maybe mention briefly. Like one use case of a multi-die is when the design is too large and you're trying to disaggregate it, right? Which is the HPC, as I mentioned. So that is not a case for a handheld device. Your design will not be so large that it won't fit on a die. The other is an aggregation case where what was put on a PCB, you're trying to put on a chip. With that, you get improved latency, improved performance. Area is not so much a concern because, it has enough space. So when the aggregation becomes economically viable and putting everything on a package, I do believe that will happen at some point. However, with the cost of the package, it may be currently economically not viable, but as the cost of packages reduce and as more application, as we try to push more edge AI into those handheld devices, it will come to a point where those will also benefit. It may just be more about economics and the benefit of going multi-die for those applications.
Okay, anybody want to add to that? Okay. So, Vishal, there's a question here that I don't know if you're able to address it in specifically this way, but I'll share it. So there are EIC and PIC die-to-die interface production, testing considerations. So The questions around production test simplifications that UCIe can offer. So I don't know if that's specifically for UCIe or if that's something that building something based on UCIe is something that helps, or if it's just maybe a different design consideration that a chip builder would have to make. Do you have any thoughts on that?
Yeah, so maybe I don't understand the question fully, but typically the EIC and PIC connection, it depends on the implementation, but generally that is not a UCIe based interconnect. It's basically the EIC driving the PIC. And so, yeah, that's typically not UCIe. The UCIe interface is usually from the EIC to the GPU or ASIC or switch on the other side. And so, yeah, that's different. I can't speak to any specific test simplification, I think was the comment. But yeah, I can't think of anything along those lines.
Okay. Yeah. So I mean, so the UCIe definitely the testing that we're putting together is for the die-to-die interface itself. And so there's things that would help a chip builder to implement their test. And for testing interoperability vendor to vendor, and that's kind of both baked into the specification itself, and then how you would go test it. But outside of that function, that probably becomes more of a function of the use case. And yeah, okay. There's some questions about where UCIe is going in the future. So we can't really comment on things that are in progress because our working groups have to work through things and deliberate and go through due diligence on options and addressing different technologies or market segments. But I would say where you're seeing boundaries being pushed in the chiplet ecosystem, that's where we're putting our attention. So I think we've addressed a number of those things in today's discussion. Manuel, did you want to jump in and say something? I don't know. You popped up in Zoom, but I'm not trying to put you on the spot where yeah.
No, but if we, I can give some comment, right? I mean, okay. If we look at what would be the next directions in the die-to-die connectivity, I think there are several. I mean, obviously one of them is following the paradigm of all the other die-to-die interface, all the other interfaces, I should say, higher bandwidth, higher speeds. That's always needed, and certainly the HPC side of things is gonna ask for that. So that is a direction, but there is direction in a sense that there would be also the opposite direction, right? Support. We talked about handheld and let's say consumer type of applications. If often in those cases, the bandwidth they are not looking for the highest bandwidth possible, right? They are looking for the flexibility of multi-die. They're looking to the ability to build different SKUs from mix and matching different chiplets, but I don't need the full bandwidth of say UCIe even standard at 64 gig. They might want to go lower speed or even lower form factors. So Synopsys. I would say UCIe Consortium already defines some smaller form factors, but typically geared more for testing, etc. But I think that's also potentially a direction how to better support that type of market once the economics, and I agree with Mayank, once the economy is there to support this direction into multi-module. I would say as finally UCIe is already moving in the direction. So when we discuss interoperability here, we discuss it from the perspective of the die-to-die interface. It's the building block. It's the most important. It's the foundational element of a chiplet system, chiplet-based system. But it's not the only one, right? You need to make sure that all the other pieces that we talked about, management, security, initialization of the system, all those pieces need to come together and be common across the different chiplets. And that's a role that UCIe is taking already, but needs to continue pushing forward.
Thanks. Anyone want to add to that?
Yeah, I think I'll just say, you know, with kind of the more recent addition of the system and package management features from UCIe, you know, it's really enabling to kind of get away from just looking at the die-to-die interface and looking at how you can actually incorporate chiplets from different vendors into a full package. And I think there's a growing, you know, sense in the industry that there's a need to really flesh out even more like how different chiplet vendors can collaborate. And so there's a lot of stuff going on in the industry with the Open Compute project and their open chiplet economy, what ARM is doing with the CSA, and all of these kind of system level, you know, how do we grow the chiplet economy? How do we enable chiplet vendors to kind of work together interdependently? A lot of it's being built around UCIe and recognizing that UCIe is one of the primary die-to-die interfaces that's out there on the market. So there's a lot of traction, I think, that's able to build on some of the more recent features that have been introduced in the specification itself.
Yeah, good point. Here's another question to see if, oh, go ahead.
Oh, sorry, Brian. Yeah, one thing I would like to add, I mean, many of the questions are about, like, can we have this application over UCI or that application over UCI? I think while it will not be correct to answer about a particular application, it is always important to remember that UCI is a layered architecture. So you can have, say, Justify, and that interface is standard called raw die-to-die interface. You can have, say, just the adapter or the streaming interface. That is another standard interface called FLIT-away die-to-die interface. Similarly, on top of it, you can have standard protocols like PCI, CXL. Also, over streaming now, a few standards are being defined. So that is the beauty of UCI. You can use it for as much or as little of the stack that you want, and you can put whatever you want on top of it as long as it meets the standard. So I hope that is able to kind of answer questions on what we can put together with UCI, because essentially the idea is this: we define standards at various levels in the IP, and as long as you meet the standard and the standard is open, it's available, then anything on top of it will work.
I think, you know, people have choices, and, you know, if you're, you know, a company looking to invest in a chiplet, you know, you have to decide, are you going to build to a spec of somebody, or are you trying to serve, you know, an open market? And if so, then that will influence, you know, what choices you're making there. So here's another one that I think several of you could comment on. So have you seen UCI interoperability between tech nodes? And what are some challenges that are specific to this scenario?
So we have, I mean, the interoperability that I mentioned. So our test chip was in a different tech node. Intel's test chip was in a different tech node. I mean, that is actually public information. We have also put out public announcements about it. So yes, we have interoperated across tech nodes, and the challenge is specific to that. I would say that given the robust spec that UCI has, they are less about heterogeneous integration, but more about general integration. So my feedback or my experience there has been that the anything that we notice was not so much about the tech nodes being different. It is more about that the files are designed, say, by different set of people. So obviously the spec defines something, then there are few things that, for example, may still be different. So those things, so it's not so much about the process nodes being different.
And I'll add to that maybe that, yeah, I think even the example which we talked about with us and Siemens and Alphawave, yeah, that was two different chips and two different nodes from two different fabs. So we were on a photonics node from one fab for our chiplet. The Alphawave chiplet was on a cutting edge electronics node from a different fab. And the whole point of UCIe is to actually work with different nodes in different fabs. If it was the same node, then there's really no point in having two different chiplets. You might as well have, you know, made them together, given if assuming the area works out like Mayank was saying. But so I think UCIe has certainly been built with that in mind.
And I think I'll just add, even beyond just the tech node, right? Even if you look at package, right, which is an important factor when you build the whole system together, UCIe really provides the framework in terms of bump map and the electrical parameters that even if you built an IP for, say, one, like a silicon interposer, you can easily use that same IP within a bridge. We've done that interoperability between TSMC and Intel EMIB, for example, where you don't have, because of the framework that UCIe provides in terms of the bump map and all of the physical parameters, that we don't have to make any changes to the IP. So even from an ecosystem perspective, right, not just mix and match tech nodes, but you're also able to kind of design an IP that can go into multiple form factors in terms of the packaging options that's available out there, which is quite critical, I think, as we start to look at more disaggregated systems across automotive, handheld. We spoke about, the different application spaces. Each of them have specific packaging requirements. And the beauty of UCIe is that, there's not a lot of change that you have to make to the upper metal layers or the IP itself. It does well as a plug and play piece of the puzzle. So
very good. We have just a couple of minutes left. I will say there were some more questions that were a little bit specific to one, company in here. We'll share that with the companies, and they can see the Q&A here. But you'll need to follow up with the vendors if you want to know a little bit more about how they're addressing market segments or particular specs or things. But I just wanted to give just another minute. If there's anything that we didn't cover, is there any panelist that has anything else that we didn't get to cover? All right, very good. Well, thank you to everybody for joining us today, spending some time learning more about UCIe and hearing real-world examples of the progress that we're making as an industry, as an ecosystem. Please come to UCIe, our portal. We have a lot of, we share some of the examples you heard about today in our blog. We continuously have more webinars and information about our member companies that you can access and learn more about what's going on with the UCIe ecosystem. And appreciate all the great questions and participation for everybody. So thanks and have a good rest of your day.